So now that we have already tried drawing out a tree diagram for a compound event, we're going to go into the calculating of the probabilities of these tree diagrams. So in example 1, each night's outcome is the result of a chance experiment, so rolling the four-sided die. Thus, there's a probability associated with each night's outcome. By multiplying the probabilities of the outcomes from each stage, you can obtain the probability for each branch of the tree. So keep that in mind. We are about to multiply every probability to get the probability of the entire branch. In this case, you can figure out the probability of each of our 8 outcomes. So for this family, a card game will be played if the die lands showing a value of 1, and a board game will be played if the die lands showing a value of 2, 3, or 4. So this makes the probability of a board game on a given night 0.75 or 3/4, right? Because 3 of the numbers out of 4 will give us board games, which means the probability for a card game is 1 out of 4 or 1/4, because if a number 1 lands, then that will give us a card game result out of 4 potential options. And so we're going to use the tree to examine the probabilities of the outcomes for the 3 days, and then we'll calculate the approximate probabilities for the remaining outcomes that we have. So I'm going to go through this very quickly because we already have it on our paper. And we're going to now list the probabilities of each one underneath. So we have board games, card games, board games, card games, board games, card games, board games, card games. So if yours does not match this, now is the time to edit and revise that we have board games and card games below every branch of our tree. And that when we started writing out the list, we were following the route of every single branch. And so these are the 8 that they are talking about that we should already have listed. So, I just want to make sure that we have all of these, because when we start calculating the probabilities, it's going to be super important that we have all 8. So 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And so now we can go ahead and put the probabilities below every single one. And so we could leave them as decimals, or we could leave them as fractions. I personally find multiplying fractions very easy in my preference, so I'm going to leave them as fractions. So everywhere I see board game, I'm going to put 3/4, so I can get rid of that. So 3/4, or you can put 0.75 if that's what you would like. 3/4. 3/4. Hopefully you have more room to write this below, because that's a lot neater. And then everywhere I see C, I'm going to put 1/4, 1/4, 1/4. Okay, let's just look and make sure we have a probability next to every single outcome on our tree diagram. And sure enough, we do. And so in order to show our multiplication, remember we multiply every single outcome on a branch. So for this one, it would be B times B times B, which I see is 3/4 times 3/4 times 3/4. Okay. And I remember that when we multiply fractions, remember we multiply the numerators and the denominators together. So that would be 9/16 times 3/4, which again, if we multiply those straight across, would be 27. And then 16 times 40 should be, I believe, 64. 16 times, sorry, not 44, I mean, should be 64. So this is the probability, 27 out of 64, of getting 3 board games in a row. Now, you may have written the decimals out and gotten a fraction of about I think it's 0.141. Let me double check just really quickly in case you did do it this way. That would be 0.422. But again, the decimal is not very nice, so I'm going to leave them as fractions and just clean up my work here so that we have more space. And now we're going to do the same process below. So BBC would be 3/4 times 3/4 times 1/4 this time. So again, we know 3/4 times 3/4 is 9/16. And then if we multiply that by 1/4, remember to multiply the numerators and the denominators together, we would get 9/64. So that would be the probability of this outcome happening, 2 board games and 1 card game. And so everywhere I see, there's a lot of repetition with these outcomes. So this op has 2 board games and 1 card game. Therefore, it would have the same probability of what we just did, 9/64. And now if I look at the one below, this has 1 board game and 2 card games. And so we haven't multiplied 3/4 times 1/4 times 1/4 yet. So let's go ahead and do that. I see that this is 3/16 times 1/4 would get us 3/64. So this is a slightly different probability than what we've had so far. And then I see the next one has 2 board games and 1 card game, which would match the ones that we just did of 9/64. This one has 2 card games and 1 board game, which would match the one we just did of 3/64. This one also has 2 card games and 1 board game, so that would be the same. And then finally, this one is different because it is all 3 card games, so we need to multiply 1/4 times 1/4 times 1/4, which actually is going to still get us 1/64. So let's stamp that when we're dealing with more complicated experiments, tree diagrams can be used to organize outcomes and to assign probabilities. Like we wrote underneath every single outcome, right? 3/4 and the 1/4. Probabilities will then be multiplied together to find the overall probability of that specific event occurring. So for example, the probability of having 3 board games in a row is 27/64. Whereas the probability of having the board game Monday and then a card game Tuesday and Wednesday would be 3/64. And finally, the lowest probability is the 3 card games in a row, which would then be a probability of 1/64. So we're going to try some more independently.